Okay, we have seen in this slide that once the information about the two surfaces for plate fin heat exchanger, all the parameters are known according to Case and London book, then we can calculate the number of plates. Also we can calculate the volume between the plates for surface 1 and surface 2. And we know that the relation that relates the area for side 1 to the volume between the plates is beta, and the same thing for the other surface. Also beta is defined as the heat transfer area divided by the volume between the plates for side 2. Now sometimes we need for sizing plate heat exchanger, we need the ratio. We need for example the ratio A2 over A1. Since it is a design problem, we do not have A2 and A1, but we need A2 and A1 in order to find the value of U. So U is a function of A2 A1, but since A2 and A1 are required for sizing compact heat exchanger, in the following slides, 2 or 3 slides, we are going to see how can you evaluate alpha 1 and alpha 2 based on the information of the parameters given for each of these two surfaces. Once alpha 1 is the heat transfer area be divided by the volume of the heat exchanger total, and alpha 2 is A2 over the volume of the heat exchanger total. So you can say that A2 على A over 1, the ratio is actually A2 over A1. So if we can find the value of alpha 2 over alpha 1, we can find A2 over A1. In the following, we are going to see how we deduce or find this relation. We start with the sigma definition, which says that sigma is equal the minimum flow area divided by the frontal area. Sometimes we call it A minimum, sometimes we call it FF to indicate free flow area for side 1 divided by the frontal area for side 1. This relation can be modified by multiplying by both sides, the numerator and denominator by LB1, and utilizing the fact that the frontal area multiplied by the length and the direction of the flow is going to give you a volume. And also you can also relate the hydraulic diameter to the heat transfer area and the free flow area. So you can substitute AFF1 multiplied by LB1 by A1 multiplied by the hydraulic diameter of side 1 divided by 4. Also, since the area 1, the heat transfer area 1, can be related to beta, since beta is equal to the heat transfer beta 1 divided by the volume between the plates for 1. So we can write also, we can remove A1 and write instead of that the volume between the plates V1 multiplied by beta, and DH, the hydraulic diameter, divided by 4 as it is. Actually we utilized this relation. I have to remove this thing. We utilize this relation which says that the hydraulic diameter, which is 4 multiplied by the flow area divided by the perimeter, multiply L by L, both in the numerator and denominator, you get 4, and then since P times L is the area, so you can say that DH is equal 4 free flow area divided by the area multiplied by L. This we utilize this thing here, since we removed AFF from this expression or from this equation and put instead of it dH multiplied by A divided by 4 and L. So actually what we did is actually AFF, the free flow area, from this equation it can be written as dH multiplied by the area. Of course we are talking about 1 since we are talking about side 1, divided by, so it's going to be dH of 4 divided by 4L. When you put this thing here, so you get this expression, and then substitute A1 with the beta, which is, as we said before, the heat transfer area divided by the volume between the plates. The volume of the between plates here is, sometimes we write it as V1, sometimes we write it as VB1, all the same thing, the area between the plates for side 1. Of course we can write it also for side 2. Beta is given, as we said before, and LB1 actually is the length of the heat exchanger in the direction of the flow. For example, you can say LB1, which indicates the flow, the length of the heat exchanger in the direction of side 1, and LB2 is the length of the heat exchanger in the direction of side 2. You can write the volume of the heat exchanger as L1 times L2 multiplied by the common edge, as we wrote it before. So the volume is L1 times L2 times, as we said, the common edge, which is given in terms of B1, B2, and NB plus the thickness of the plate. Sometimes we write A minimum, and sometimes we write it AFF, which indicate the same thing. That is the minimum flow area or free flow area. Now go back to this equation, which is alpha sigma, and put in the volume this expression. You take the volume for this expression for sigma and substitute with the volume with this expression. So you get V1 B1 dH1 divided by 4 divided by the volume, which is given by this equation. Also, since V1, the volume between the plates, it can be written also in terms of L1, L2, B1 and NB. So we can write also V1, the volume between the plates, by this expression. Notice that actually we are going to assume that NP and NP plus 1 is almost the same. The difference is very small, especially for very small spacing, B1 or B2. So now we have an expression, very long expression, that gives you sigma. You can take L1 with L1 and L2 with L2. You can take NB as a common factor here also, and then you can reduce this above equation into this equation. So you get B1 times beta multiplied by the hydraulic diameter for side 1 divided by 4, and then the whole thing is divided by B1 plus B2 plus 2A. You can do the same thing also for side 2. You can write also sigma 2 as, and you change, take beta 1 is going to be beta 2, hydraulic diameter is going to be 2. Now alpha, as we defined it before, is the heat transfer area divided by the total volume. Notice that this is the total volume, not the volume between the plates. So we can write it A times A frontal for side 1 multiplied by A L1, which is also the length in the direction of the side 1 flow. And also we can go back again and utilize this equation to write A1 in terms of the free flow area and the hydraulic diameter. And then also, since the free flow area divided by the frontal area, I mean this ratio, is actually sigma. So you can write sigma instead of the frontal area divided by free flow area, I'm sorry, divided by the frontal area. This one is sigma 1, and 4 as it is 4, and dH then we'll go back it and put it in the denominator. So we have now another expression for alpha, which is this one. Now take sigma, which is the minimum flow area divided by the frontal area, from this expression and put it in this equation, so you get the expression that we are looking for. This expression is very important now, which gives you alpha in terms of B1, B2, A and beta. So if you know the surface, you can actually find alpha in terms of, as we said, B1, B2, A and beta, which is a very, very important conclusion. Of course, we can do the same thing for side 2, do the calculations again, and you get another expression for alpha and sigma. So alpha 2 is going to be this expression, which is what we are looking for. The conclusion of these two equations is that now you have alpha 1 and alpha 1 as a function of, as we said, B1, B2, A and beta 1, and you have alpha 2 is a function of also function of B1, B2, A and beta 2. So you can calculate alpha 1 and alpha 2. You can get how much is the heat transfer area divided by the volume of the heat exchanger, and then you can find also A2 by A1. You only divide alpha 2 divided by alpha 1. This is a very important conclusion that is going to be used in sizing plate fin heat exchanger. As we said before, B1 and B2 are only spacing, and NB is the number of passes. This is what I actually am trying to say. This slide also just repeat what I said before, is that if you could find alpha 1 and alpha 2, then actually you can find the area ratio alpha 2 over alpha 1, which is equal to A2 over A1, and then you can utilize it in the expression for the overall heat transfer coefficient. For example, this expression shows the overall heat transfer coefficient based on the side 1 area, which is 3 terms. This is internal, this is heat transfer, convective heat transfer for side 1, convective heat transfer for side 2. Of course, for plate tube heat exchanger, we have fins at both sides. So you have eta 01, which is the overall surface efficiency for side 1, and eta 02, which is alpha, which is the overall surface efficiency for side 2. RW is the thermal resistance in the wall, which can be written written as A, which is the thickness of the plate, divided by the thermal conductivity multiplied by AW. AW is the wall area, which is going to be written by this expression. Of course, you can find the overall surface efficiency utilizing omega 1 and omega 2, omega 1 and eta the fin efficiency, and this is omega 2, which is the ratio of the fin area divided by the heat transfer area, and eta F2 is the fin efficiency. Of course, for most of our calculations, we are going to assume that the fins are straight fins, so we can utilize this expression to find the fin efficiency, which is tanh MLF divided by MLF, where M is under square root 2H divided by KF multiplied by DF, where H is the heat transfer convective heat transfer coefficient, Kf is the thermal conductivity, delta is the thickness of the fin. LF is LF here, this one. LF actually is the length of the fin. We usually take it as half of the spacing between the plates. So in many cases we can take LF, the thickness or the length of the fin is to be, for example, for 1 is going to be B1 over 2, and LF, and this is equal to LF2 equal B2 over 2. so half of the spacing. And delta F is the thickness of the fin that is given usually among the data of the surface. If you go back to this equation, and neglect the conduction, the conduction resistance, this one, and you multiply the whole equation by A1, you get this expression. So you get 1 over H1 eta 01 plus 1 over H2, and then the ratio A2 divided by A1 multiplied by the overall surface efficiency for side 2. And as we said, this now can be found since we have calculated alpha 1 and alpha 2. So the ratio A2 over A1 is going to be as given here, which is alpha 2 divided by alpha 1. In conclusion, of the 3-4 slides that we have seen up to this point, is that knowing the two surfaces, knowing the information about the two surfaces, you should be able to find the number. Also, if you know, you can also calculate the several parameters, among them sigma 1 and sigma 2, and alpha 1 and alpha 2, from which you can find also the heat transfer area ratio, which is A2 over A1 as a function of alpha 1 and alpha 2. The pressure drop for plate fin heat exchanger, gas to gas heat exchanger, in some textbook it can be written as this, similar to this expression, but notice that it has now 1 term, 2 terms, 3 terms, 4 terms. Of course, this term we know it, which is due to friction, and this term actually we know it since this is due to acceleration, deceleration. This term is due to the entrance pressure drop, and this term, the fourth term, is due to the exit, if we have some kind of pressure drop due to exit condition of the flow for either side, side 1 or side 2. The average density, actually, notice that here the density, if you have rho I is the density at the inlet, rho 0 or rho O is the density at outlet, and rho without anything is the average density, which is the average of the two. Now we are going now to talk about procedure, general procedure to rate a given gas to gas or plate fin heat exchanger. We are going to assume that we have a box that has two fluids, gases, both of them, entering at different temperatures, and the mass flow rate is given for each of them, and the side for each one of the given, I mean the surface, according to Case and London. So you know the surface data for side 1, and also you know the surface data for side 2. Also given the dimensions. So you can get the frontal area for side 1 and the frontal area for side 2. All the dimensions of the heat exchanger are given, and from the Case and London you can find all the data for that surface, like for example the hydraulic diameter, the plate spacing, the fin thickness, the beta 1, omega 1, and also you can calculate alpha 2. The same thing for surface 2, all the data are given to you. We are thinking about a problem similar to the following. Suppose that everything is usually now is given, surface 1 is given, surface 2 is given, length are given, all of them, and the frontal area is given, the mass flow rate or the volume flow rate is given for side 1 and side 2, and also supposing this is the hot fluid given at temperature T hot inlet, the temperature of cold temperature also is given inlet. Required now, the requirement is how much is Q is transferred between the hot fluid and cold fluid. How much is the temperature that is going out from the hot fluid, and how much is the cold fluid outlet temperature. In addition, to the pressure drop for side 1 and side 2. So if it is, the heat exchanger is given with all the dimensions, so the heat exchanger is there, and only we need just to experiment this heat exchanger with given fluid number 1 and fluid number 2. Fluid number 1 is a hot fluid, here is the gas, and fluid number 2, which is the air. And we would like to calculate these parameters. How much is the heat is transferred now between the two fluids? How much is the outlet temperature for the hot fluid? How much is the cold outlet temperature for the cold fluid? And what is the pressure drop for side 1 and side 2? Suppose you know the surface 1, you know everything about it. In addition to surface 2 also, surface 1 and surface 2, both of them you know everything about them. And you know also the curve that relates Reynolds number with friction coefficient and J for this surface, and also you know also the friction coefficient JH for this surface also, for surface 2. So you know everything about surface 1 and surface 2. Our objective now is just to rate this heat exchanger. Rating meaning that tell us how much heat is transferred, tell us how much is the outlet temperature for side 1 and side 2, in addition to the pressure drop. Okay, the procedure is that you can go ahead and calculate the number of passes, number of plate, and also you calculate alpha 1 and alpha 2 as we did before. So everything is known, you can proceed, see how many number of plates in terms of B1, B2, and the common edge. Of course here the common edge is, as you can see, the common edge is L3. The frontal area for A1, for side 2 is L1 times L3. The frontal area for side number 1 is L3 times L2, and it is obvious that this is the common edge. And since you know beta 1 and beta 2 and the thickness of the plate, you can find also the number of plates, alpha 1 and alpha 2, as we did previously. You can calculate the volume between the plates, since you know everything about the surface 1 and surface 2. You can calculate the heat transfer area, since beta is known. If beta 1, for example, beta 1 is A1 divided by the volume of the plates 1. Okay, now since you have calculated the volume between the plates and you know beta, so you get A1, and the same thing for A2. Number 4, you know you could be able to find the frontal area for 1 and frontal area for 2. Use sigma. Sigma is minimum free flow area divided by the frontal area. So since sigma, of course sigma 1 or sigma 2 is known, and the frontal area is known for side 1 and side 2, so you could be able to find the free flow area, or sometimes we call it the minimum flow area. This area and this area. The minimum flow area for side 1 and side 2. Once you did that, you can calculate G. Okay, G, we have said that G, the mass velocity, for example G1, is equals, by definition, Vmax rho multiplied by Vmax. Or it can be written as m dot divided by sigma times A frontal. If you talk about 1, so this is 1, 1, and 1. So if you divide the mass flow rate divided by sigma multiplied by the frontal area, you get G. You do the same thing, of course, for side number 2. So now in step number 5, we have calculated the mass velocity for each of the two sides. Of course, once you get G1 and G2, you can also evaluate Reynolds number 1 and Reynolds number 2. We said before that Reynolds number 1, let me write it here down, Reynolds number, for example, 1 or 2 is equal to G multiplied by the hydraulic diameter divided by the viscosity. If you talk about 1, so this is 1, 1, 1, and 1. So G1 multiplied by the hydraulic diameter 1 divided by the viscosity of the fluid in side number 1, you should be able to find Reynolds number. Use this Reynolds number to go to the chart that relates the friction coefficient and the J factor with Reynolds number. Calculate JH1 or JH2, also the friction coefficient number 1 for side number 1 and friction coefficient for side number 2. After that, then you can, since JH is known now, you should be able to find the heat transfer coefficient H1 and H2 very easily. Of course, one step that we did not say, but it has to be done, yani, which is that the properties like the viscosity, the specific heat, the Prandtl number, and so other and others, it has to be calculated based on some average temperature. Of course, we do not have an average temperature, since we have only the inlet temperature for the hot fluid, and we have only the inlet temperature for the cold fluid. So some temperature is going to be assumed for the side 1 gas and side 2. Other things that has to be also noticed is that the pressure. If the pressure is given, then the pressure, then you have to take care of the density calculation. It has to be used, for example, ideal gas law to find the density. Ideal gas law says that rho equal to P over RT. So if the pressure actually is not is given, then you have to calculate the density. And the density is a function, as we see from this expression, which is the ideal gas law, is a function of the pressure and temperatures. Other properties like the specific heat, the thermal conductivity, Prandtl number, and viscosity is a function only of temperature. This is what we do usually in our calculations. Going back, just remember that you have to calculate all the properties that you need. As you said, specific heat, thermal conductivity, and so at some average temperature. Maybe it's going to be revised again after you do the first trial. Also, you have to calculate the efficiency and the overall surface efficiency, because you are talking about now both sides. We are talking about plate fin heat exchanger. We have fins in this side and fins in the other side, so you have to take care of that and calculate the fin efficiency for both sides and the overall surface efficiency for the surfaces. Once you calculated all these parameters, you can go back and substitute in the equation for U value. Of course, one thing I didn't say here, but the heat transfer areas has been calculated in step number 3. So it's easy to calculate the U factor in step number 9. You can calculate Q max, since the inlet temperatures are known, the mass flow rate is known, Cp cold fluid, Cp hot fluid are known, so you could also calculate the Q max, which is as we defined before, which is equal to C minimum, multiplied by delta T maximum. So let me write it here down. This is equals C min multiplied by delta T max. Which C min, we have to find capital C for the side 1 and capital C for side 2. Of course, C capital 1 for the hot fluid, for example, C hot to C1, because this is side 1, equal to M dot 1 times Cp1. And the same thing here, you can write C cold equal to C2, which is equal to M dot 2 times Cp2. And you see which one of them is minimum, which is lower the other one. One of them is C, we call it C min, and the other one is C cold. You take C min, multiply by delta T max, you get Q max. Calculate CR and NTU. Of course, we know that CR is the ratio C min and C max, and NTU is equal to U multiplied by area divided by C minimum. Then get the effectiveness. Calculate the heat rate. Of course, the heat rate is, since Q max is known, the effectiveness is known, so Q is going to be the effectiveness times Q max. Calculate the outlet temperature. Of course, once Q is known, because Q actually Q is equal M dot Cp either cold or hot, multiply by delta T cold. You can get the T cold out, and the same thing you can get the hot temperature outlet, which is required in this equation. So we calculated Q, we calculated TH out, T cold out, and now we have to go and calculate the pressure drop, since we have get the friction coefficient for side 1 and side 2. Then actually you can calculate the pressure drop for both sides. this is a very fundamental idea for rating